My name is Yuan. It's my name. And these are my students. Really work will be done by, most done by students. Okay, 43 students finish a PhD work already. They work in different around the world. And the last two are still active. Today, I'm going to talk about the major results from these 3 students. And the title of my talk has been modified slightly, add fatigue damage into the title. I want to concentrate on the discussion about fatigue. Good, and that's the outline of my talk. And just a few words about background, then microstructure analysis, and anisotropic materials properties, anisotropic in material. If you're talking about additive manufacturing, usually we assume materials are anisotropic. How the material is anisotropic, we going to show something, and then about damage and the fatigue assessment and so on. Good. And okay, in past 3 days, we heard a lot of lectures about additive manufacturing. But my image actually made research reporting in the conference dealing with materials technique and structure, something else. But actually, I'm worth air engine designer. I'm responsible for engine design. So I'm interested actually not on the materials microstructure itself, but I'm mainly interested in materials property application. Therefore, my question was at the time, as I see this technique, is actually, how can I use this material for my heat engine parts, for instance, for rotating parts? That will be the most important question. If you tell me the material property from AM is the same, even better than the sort of forged material, that will be a great thing. Therefore, for me, I'm really interested to know, to quantify the difference of the material from additive manufacturing in compared to forging, for instance. Actually, we are concentrated so-called incandescent 18. Incandescent 18 is the most popular material, most important superalloy in the turbine industry. Okay, incandescent 624, 25, the other mainly cast material in the sense. And incandescent 18 is actually usually a forged material. It's used for rotating parts actually. Okay, therefore materials property becomes very important. In that case, okay, this picture to show you actually the application. It was said actually this kind of material will be used in engine design, but in reality it's actually the AM material parts are mainly statical parts. The reason actually we are not conformed, we are not convinced to use this part for rotating parts. Rotating parts are much more dangerous, much more important. If rotating disk split, burst, whole engine, not engine not engine is destroyed, perhaps the whole airplane can be shut down. Therefore, it is very, very important in the case to know how the material property of the material. Okay, we started with the conventional form to check the isotropic, that means you print material different according to the EOS standard. EOS developed different printing strategy for different materials, also for different parts. We use actually standard EOS strategy. We assume EOS are much more experienced than what we can. Therefore, we do not try to optimize the print strategy. And also heat treatment, actually, in the case we use actually standard heat treatment procedure for incandescent 18. There's also standard for incandescent 18 how to heat treatment. And originally we introduced actually a standard effect of HIP. And that is actually, therefore we have 3 different states. As built, that is our original specimen. And the specimen actually looks like this form, but this is the original specimen. This specimen will be turned into the certain form for testing. Nowadays, we can produce also the plate form to study actually, in fact, the thickness effect of the specimen. And then, okay, that is the so-called homogenization plus solution plus aging. That is actually standard incandescent 18 procedure. And finally, HIP charge plus homogenization solution strategy. That's actually HIP is actually additional state to eliminate or to reduce actually the porosity of the material. Okay, 3 different angles we checked, and then Okay, we rotate actually always rotate in 67 degree in each layer. And the layer thickness is supposed, oh, I forget, 40 microns actually. That is the standard actually we used in the part. Okay, microstructure looks very different. Of course, the AS state is microstructure is very similar. EBSD figures more or less the same. The reason actually we do not want to change the green distribution first. Okay, after HIP, of course, the whole structure becomes very different. If we check the three pictures, we see, okay, HIP should have very different property as comparison. That means in engineering design, usually we are familiar with the International 18. That means data from International 18 is available for engineering design. Therefore, we use this as a criteria. That means what we want to see is actually to see the difference between AA material to my known material International 18. You see that is, you see this International 18 is a very fine grain material. That means grain size around about 10 microns. Here you see larger than 100 microns. Now, would say, okay, this material must be much worse than International 18. That's our image actually immediately, right? And then reality is actually different. Okay, that is the distribution of the grain size as a function of the frequency and so on. And what we see is actually, what we see, we'll come to the picture first. That is actually the stress strain curve, stress over strain. You see that is our International 18, conventional one, that is as built state. We see, okay, very significant difference. The material becomes much weaker in compared to the forged material. After heat treatment, we reach actually the level of International 18. Difference, less than 10%. That is actually, for engineering design, it is acceptable tolerance. Okay, after HIP, that seems not so very different. It will be interesting to ask why this happens. We see very different microstructure figures, right? We see from the grain size and so on, from AM is much larger than forged material. And if we check this material, that is the printed material, printed material. What we see is actually that is the grain size. We see that's the grain size here, the grain boundary here. What we see additionally with this kind of very shallow different figures. That's actually in tin, you see this kind of cells, a lot of macro cells in nano size, around about 0.5 microns. That means around about 100 nano. That is actually the black line show you actually the dislocation boundary. They build actually additional structure. Okay, this is 1 grain, but under grain you have macrostructure in it. This is very typical actually in a superalloy. We see this kind of structure not only in this print material, we can also see this kind of field also in cast material. We see also this kind of structure. Therefore, in that sense, grain size affect material's property, but it's not dominant case. What we see is actually in the macro scale, we see these features, they are actually not affected by grain size. Therefore, even after HIP, the grain size change suddenly again, much severe again, but the stress strain curve looks very similar. Okay, that is a picture showing again that is in different state we have similar pictures. Okay, the next point, of course, if we want to design our mechanical components, we need, of course, also the whole stress strain curve. We performed tension compression test or monotonic test. That what we see is actually this solid line. See what is solid line? Solid line is actually monotonic curve. That is the different directions. We have 3 directions: 0 degree, 45 degree, 90 degree, and that dashed line show you actually cyclic stress strain curve. This features looks also comparable to the forged material, and you see, okay, compare here again. Therefore, stress strain curve looks actually similar. We see slightly difference in different orientation. Okay, Harry. Okay, the question is actually how to develop the stress strain constitutive model. We have a cyclic process model based on one consideration, we changed actually the yield condition. That means that is a yield function f. Okay, we introduce actually the weight according to the Hill method. Okay, we assume actually the weight function is a function of plastic strain to apply them for cyclic plasticity. That means F here, F1, F2, F3, and F7, they are not constant. They are a function of plastic strain. That's just empirical, phenomenological fitting. Okay, anyway, the results looks very interesting. Okay, we see the comparison between the experiments to computation. We perform a cyclic monotonic multiple, that is no proportional cyclic strain curve and so on. Even you have cross form, and agreement is reasonable. It's actually for industrial application would be is good enough. That means the material's property is slightly anisotropic, but we can use the conventional model with modification to cover this form. Okay, the materials of course contain many porosity in the material. Okay, after HIP, we see okay the surface becomes clear due to the high pressure, but in the center we still have this kind of porosity voids. Okay, and but how to quantify the effect voids is actually still an open issue. The reasons actually we found. Yield stress seems very similar to compared to inclination 18, but the fracture strain is much smaller, right? About 50%, less than 50% in compared to the inclination 18. Therefore, how to quantify the effect is still the issue. Okay, that is a topic going to when we continue investigating. We see the many different tests. Okay, we developed the so-called damage method. That is a conventional damage form. We use also the scalar parameter to quantify this effect. And this model can be used for monotonic and acyclic stress strain curve. Okay, the total damage will be decomposed into plastic part, the cyclic part. You can also find the correct comparison between the tests two curves. Okay, skip something. That is stress strain curve here. You see the small distribution in different three directions. You have a large small scattering. That is this outline show you again inclination 18. These results are from actually A material. Okay, if you use what it depends on actually what kind of variable you use. If you delta epsilon as a variable, you see the scattering becomes more significant. But this effect can also be eliminated if you modify you use actual multi-axial fatigue model. The scattering is actually within factor 2 band actually more or less. Therefore, in this sense, material is actually not so worse. Okay, one open issue is actually how to quantify the effects of macro defects. This will be studied right now, and perhaps next in 2 years I can show you more results. The conclusion in one sentence. The material is much better than we expected. Actually, we can use it for rotating parts. We are on the way trying to use it. Thank you.